Some of the college students and research experience. So what we're trying to do is to extend that to the high school level with our project called SALAD. That's the Salinas Air Shower River and Discovery Project. So what we're going to present today is our what we will be showing the high school students through our detector setup, our signal comparator circuits, as well as using Arduino as a microcontroller.
So this is actually what we want the students to be building. It is the detector circuit and a power supply circuit, which would eventually be on this board. They're going to need to be able to line things up, and it's a lot of fabricating, and it's quite delicate, such as in here. I'm not sure why this box is here, but this right here is quite a little bit delicate work. So they are going to need some supervision, but in our increasingly technological society, these are skills that up and coming people entering the workforce will need. So this detector is 3 by 3 millimeters. So it's very, very small, and it does pose a challenge to build. So we might use something that's a little bit more robust, because I myself, prototyping this, had some problems with that particular detector. But overall, this is what we want the students to build. It's a very sensitive light detector. It detects down to a single photon, and we use cosmic rays to actually stimulate the detector through a scintillating piece of plastic. Eventually, the entire assembly goes into a box that the student will have drilled the appropriate holes into. This is the circuit that they build, and also part of the process is for them to test the circuit once they're finished constructing it, and hopefully not electrocute themselves and be turned off by to the process.
In my portion of the project, I'm going to be helping them with the data acquisition. So I'd be working with the comparator circuit board that they'd be working with. So we hope that they can test the comparator circuit board using a DC signal to see if it works, and to simulate cosmic ray going through the scintillating plastic using a pulse generator. So this is a setup that we tested to see what comparator would work best for them in order to use. So right here, what is shown is a circuit board. This is where the input would come in from the detectors. The analog signal would turn into will be converted to a digital signal, and then the LMH 6559 would give power to the signal, so you can see it on the oscilloscope. And then from there, we hope that they can, from using their reasoning skills, which comparator would work best. And we hope that they can see these results as well. For example, this one's the results for the pulse generator for the 8561, and this is the results that we get from the DC input from the 8561. And then hopefully they can see how these graphs are different from one another, because the previous ones didn't really need that much more addition of voltage to turn off and on, while this one was more gradual. And we hope that they can see these pulses that are created by the circuit. And then after they start getting used to this circuit board, we want to take them to we want to step it up a level where we have 2 comparators and logic. So whenever there's a coincidence between the 2 detectors that we give them, they can get an account. And we have them test it out by giving it a pulse in both the first and the second comparator, and so they can see how this works. Let me see how this works with the output. With the first comparator there, the second, the AND logic, and they can see that there's a signal being produced by the comparators.
And now comes to my part of the project, which worked after the acquisition to display it. As Daniel explained, once we get a trigger, we need to have some way to count these triggers over time so that we can compare them to some of the data that we've taken ourselves, but with the high school students. So before we had a very complex setup that involved some NIM modules, and we've brought it down to a simple level. So my first experiment involves a trigger that set the function generator to trigger at 1 hertz, and then I would observe that over the oscilloscope, and then on my setup on this digital lab, it has an Arduino as well as an LED display in the controller. So this is a simple diagram of how my first setup had. So according to the manufacturer of the Arduino, it required 100 microsecond pulse width in order for it to actually read. So in order to test that, I just fed different pulse widths down from 40 all the way up to 200. It read faster for whatever reason, but at 100 microsecond pulse width, it read very near what I should expect at 1 hertz, 100 counts in 100 seconds. So this is my setup that's on the digital lab. The pulse that we read in through one of these ports would be fed in through the Arduino, and then that would send signals to the MAX7221 LED driver and then display directly on the LED display. So this is my setup with the Arduino. It uses just 4 pins, 3 of them to communicate with the MAX7221, and then 1 to get data read in from the through our testing the pulse generator, but it can also accept the actual logic signal from the comparator and the AND logic gate. So how the code works, I have little snippets of it in the background, is once it gets the data read, simple count goes up by 1. If it is more than a single digit, it's split up into its individual digits and then displayed. So this is a close-up of the 7221 LED controller and the display that we used. And again, just a little snippet of the code of how each of the individual digits are displayed. So once it gets a trigger and it sends these signals, this is an example of some of the signals coming out of the Arduino getting sent into the controller, just to test that and make sure because they had some control data of what they should look like, and they look exactly the same. So in conclusion, we're hoping that all of our concepts as well as our methodology can be easily taught to the high school students. And just recently, we visited one of the local high schools and presented them. And we have somewhat about 12 students that are not only interested in our research and I guess more of physics research as some kind of opportunity, but they're also willing to join us for 2 weekends worth of some very fun work. Thank you.
How do you get involved at the high school, or how do you talk to the science teachers to get involved?
We actually have some there's some high school teachers that also teach some classes at our community college. So we really just connect with them. Otherwise, we would go to all the several community high schools that are willing to work with us. Yes.
Have you looked for funding? Because I proposed exactly this in my last NSF proposal. Are you guys also soliciting funding for this, or you have enough money to pursue it? And
I believe through our project, our initial project, we were working through a Title V grant, but I'm not. You have to talk with my mentors in the back about how we're funding for the high school project. I'm not completely sure about that.
Okay.
Yes.
How much did this students do, and how much did you do?
So we set up just some of the build-up, which is, so we're all doing it at the moment, but we're deciding, they're going to be doing a lot of the soldering, the drill work. I would also show them how all of the coding works. They would be replicating all of our work almost exactly.
So you haven't implemented it yet?
Yes, right. It should be somewhere in the next couple months, actually. Any other questions?